OpenStack Physics, Chapter 25, Geometric Optics. There's a bunch, like all chapters, there's a bunch of stuff, and it's kind of hard to cram all that stuff into one summary video, but this is the summary video for OpenStack College Physics, 2nd edition, and we're on Chapter 25. So read the chapter, and this is just a summary, and I'm not going to cover everything, I'm just going to go over the big things. The first thing that we kind of need to talk about that's implied, but I want to be explicit about it, is how do we see things? So here's a situation. Imagine that I have a flashlight, like that, and there's my bulb. And so this, and I'm standing over here. I'll be right up here. That's my eye, right? So my eye's right there, and the light goes this way. So what do you see if you look at the light from the side? You know, and it comes to this idea that we humans have, this idea of vision, where vision is something you do. It's something coming out of your eyes. But instead, vision is about what comes into your eyes. So if the light's going this way, and it's a beam, then you don't see anything. You don't see it. Okay, you can't see the light traveling from the side. It's not a stream of water that you're looking at. It's light. That light has to enter your eye. So if light has to enter your eye to see things, let me show you. I have a demo. Flashlight. So I'm going to turn it on. So if I hold it up just like this, like that, you can't see the light, right? Unless I point it at the camera. So now you can see it, now you can't. Now, yes, it is true that if I take some chalk dust, you can see the chalk dust, okay? And there's stuff in the air that sometimes you can see that beam. Oh, that looks really pretty nice right there. And if I get it even more this way or more this way, you can see it. Okay, but you have to have the light come into your eye to see it. Now, the next important thing is, what if light doesn't come into your eye? What if no light comes into your eye? In this case, if this is a completely dark room and there's nothing reflecting off anything and there's no light coming into your eyes, we see the color black. And that's why if you're in a dark room and there's no light at all, it looks black. Human eyes are pretty good at seeing very, very low levels. So even with a tiny bit of light, your eyes will adjust and be able to see something. But if there's no light, black. Okay, that's important. Now let's talk about reflection. So I could see something. Let's go back to my flashlight example. Here's my flashlight. And I put a ball right there. I can see the ball because light comes here and it reflects into my eye. If the light reflects into my eye, then I can detect that. Now we actually have two kinds of reflection. I didn't bring a mirror. That's weird. Okay. So we have reflection off of smooth surfaces, like a mirror, a normal mirror. And so in this case, when light comes down, and I'm drawing a light ray. So remember, light is a wave, but we can represent the propagation of these waves with the ray. So it's a light ray. So this is going to hit the mirror at some angle with respect to the normal. We'll call that theta 1. Reflect off with some angle theta 2. And theta 1 equals theta 2. So we say that the angle of incidence is equal to the angle of reflection. That's how mirrors work. Okay. And it's true whether the mirrors are curved or flat, as we'll see. Now, what if I have something like this chalkboard? It's not quite smooth. So you can represent a chalkboard as some uneven surface like that. If I have light coming in, that ray is going to reflect that way. This ray is going to reflect, let's draw that like that. This way. This ray is going to reflect this way. Okay, so we'll get parallel light rays coming in, but they reflect in all different directions. So this is a flat surface. Okay, you can see the reflection in all different directions. They don't talk about that too much, but it is kind of a big deal. Okay, next. Remember, this is a summary. I'm not telling you everything. You got to read the book. Next, speed of light. We talked about this before. They give some ideas about how you could measure the speed of light, and I have some better data on that too, a better presentation. I might show you that, I'm not sure. But we say the speed of light is approximately 3 times 10 to the 8th meters per second. But, where to put it? It turns out that the speed of light is a wave, and you can't cancel a wave, but you can get the waves to interact with atoms in some materials that they produce their own excited electromagnetic waves that interfere, and they produce slower light. So in certain materials, we have a speed of light that could be slower, let's say less than c, and we can describe the different materials with what we call the index of refraction. The index of refraction, I'm just going to put index. The index of refraction is the ratio of the speed of light to the speed in that material. So since this is less than the speed of light, this is going to be a number greater than 1. So the greater the index of refraction, the slower the speed is in that material. And that's part of the thing that causes things to happen with this. I do have another speed of light demo, and we can kind of see it. I'll pop it over here. This is a range finder. It's kind of cool. It says, I don't know what brand it is. So I'm going to turn this on. Turn it on. Okay, it's on. And what it does is if I point it at something like this with a laser, and I measure, it says, read that, 0.91. It tells you the distance from here to there. And now how that works is kind of amazing. It sends out a beam of light, and it measures the time it takes for that beam to come back. If you know the speed of light and you know the time, which is super, super, super short, okay, then you can determine the distance. And if you put that through this, I can't really do it because I wouldn't hold it completely steady. But if you do that, you'd get a different reading because it would think it's going further distance because the speed of light's slower in this material. I don't even know what this is. Acrylic plate. Okay, and that's kind of cool. Now, I can't show you because this is my phone right here. Many phones do this same thing. They can measure distances with the speed of light, and it's called LiDAR. And you can do some really awesome stuff. You can measure a 3-dimensional picture of a room with LiDAR from your phone. It's kind of a big deal. It's kind of awesome, so I love it. But this is LiDAR too. It just gives you one distance. The old kind of LiDAR would just scan this across, right? You'd scan it across something. Okay. Next. So what happens when light goes from one material to another and the speed changes? So if I have down here n equals 1.2, n equals 1, and light comes in, exaggerated view, theta 1, theta 2. So light is going to bend, and we call that refraction. Why does it do that? It's because it changes speed. And there's the classic example of an axle rolling on cement, and then it hits grass, and if one wheel slows down before the other, it causes the whole thing to turn. The same thing here. Now, the nice thing here is it doesn't matter which way the light's going, it's going to take the same path, but we can make a relationship between these two angles based on these index of refractions, n1, n2. n1 sine theta 1 is n2 sine theta 2. This is called Snell's law. So if I know the indexes of refractions and the incident angle, I can find the refracted angle, or maybe I know the two angles and I can find the ratio of the indexes of refraction. Now, something really cool happens if I'm going the other way. So let me just have my laser beam coming like this. And this is n equals 1.5, n equals 1. When you're going from a higher index of refraction to a lower one, it's going to bend away from this angle. And it's possible that you could bend it so far that theta 2 is 90 degrees. And when that happens, it's called the critical angle. And it's really kind of amazing. But the light will come here, and none of it will pass through. None of it will go into the material. You can get reflected light, but none will pass through. Okay. and that's called the critical angle. Dispersion. You've seen these rainbow things. If I take Roy G bit of light, let's put it back over here. This is the classic example. So if I have a prism and I shine red, orange, yellow, green, blue, violet light in here, I got to come in at an angle. It's going to refract and refract again, leaving. And it turns out that the index of refraction does depend on the wavelength. So longer wavelengths have lower indexes of refraction than shorter wavelengths. So what happens is you get the different colors bend different amounts: red, orange, yellow, blue, and so forth. And that's called dispersion. Okay, we're ready for the important stuff that you all came for. And that's lenses and mirrors. So here is a dirty converging lens. Okay, so we can do a whole bunch of cool stuff with this. But the first thing that we need to understand is that we can calculate. Imagine that I have a converging lens like this. I keep losing my best chalk. There it is. Okay, here's my converging lens. And I have parallel light rays coming in. These will come and all meet at the same point called the focal point. So we can measure the focal point of the lens. There is a way to calculate that based on the radius of curvatures and the index of refraction, but that's not in this chapter, and that's fine because it's a little too complicated. That's the focal point. Now here's one thing that I actually didn't know. This is also called the power is 1 over the focal length. So the focal length is measured in meters. The power is measured in diopters. Okay, so it's just 1 over the focal length. I never used that before. The book uses it, and I was like, what's that? So it's not a big deal, but it's used in some other things. At least I never used it. Never really did a lot of optic stuff. Now, we can make a real image, and I'm going to show you a simulator, a real image with a converging lens. Let's see if I can do it here. Probably can't see that. You can see that. So I'm creating an image from the window over there onto the board here. When we have a converging lens, there are 3 principal rays that we can draw. So here's my converging lens. Here's the focal point. I can draw that focal point on both sides. I'm going to draw that as a dot. Now I'm going to draw my object as an arrow. I can draw 3 principal light rays. The first is if I draw a light ray that comes in parallel to the axis, it's going to pass through the focal point. Second, if I draw a light ray going through the center of the lens, it will just keep going through the center of the lens. Now, right there, if I have those 2 light rays crossing, if I look at it from this side with my eye is dumb. I can't tell where the light rays come from. I mean, where they really came from. It looks like they come from right there. So, and in fact, I get an image right there. I get a real image. And I can project that onto a screen and everything. And then finally, the other light ray, I can draw one that goes through the focal point on this side, and it will come out parallel. And they should all meet right there. And I'll show you a better thing with this in particular. So this is my focal length. The book calls this the object distance. I'll put it down here. DO for object. And this is DI, the image distance. Now, there is a convention here. For converging lenses, the focal length is positive. And this is the positive side for objects, and this is the positive side for images. Okay, so if I get a negative image distance, it'd be over here on the opposite side. You can indeed get negative images, and I'll show you that in a little bit. Is my going too slow? I think it's working okay. I hate to redo these videos. Okay, the next is a diverging lens. So it looks like this. That's a terrible diverging lens. Like that. So in a diverging lens, we have a negative focal length. And if I have an object over here, then it's going to diverge away as though it came from that focal point. And that one's going to go that way. And here you can see that the light rays actually never cross. I'm drawing that one backwards. And so, but it looks like the image is right there. So overall, let me show you the equation for these two things. And then I'll show you the simulator because that'll be nice. 1 over f equals 1 over di plus 1 over do. So this is the focal length, the image distance, the object distance. And it's possible some of these are negative. In a diverging lens, that's negative. We also have the magnification is negative hi over ho, or di over do. So this just tells you how big the image is going to be. Negative, if you get a negative magnification, that means it's inverted. So an inverted, yeah. I don't actually, why is that like that? Yeah, because this would have a negative. Well, let's just do it anyway. Okay, let's switch to the simulator. Okay, this is the PheT simulator. It's really useful. Here we have an object, a converging lens. These are our focal points. So you can measure this distance. You can actually measure these things. They have rulers over here. You can measure things and do cool stuff with it. But here's my object distance, and we see that light comes. I want to just write my principal. Here's my 3 principal rays. So the first one comes in, passes through the focal point, one goes straight through, one goes to the focal point on this side. And where they cross, I'm going to have the tip of my image. The same thing, right? But notice that it's a real image because the light rays actually cross, and it's inverted. And so with just a single lens, if you have a real image, it's going to be upside down. What happens if I have this closer than the focal length right here? You'll notice that now these 3 rays pass through in such a way that they do not actually cross, but my eyes can trace them back and it looks like it's over here. That's a virtual image because they don't actually cross there. You can't project that onto paper. Also, this would be a negative object distance because it's on the wrong side of the lens. If you want, you can put this as a diverging lens, and you can see here that there's nowhere I can put this that would make a real image. Okay. So you should play around with that because it's pretty cool. You can also do this as kind of nice there's many light rays, right? They don't all pass through the lens, but there's that. Okay, mirrors. Let's go back over here. We have 2 kinds of mirrors, well, 3 kinds of mirrors. You have flat mirrors. So a flat mirror like this. If I put an object right here, I can draw a light ray that goes there, and it's going to come back. I can draw a light ray right here, and it's going to make equal and opposite angles, and then I can trace these back, and I get an image right there. So the image distance is the same as the object distance. It's behind the mirror the same amount. That's why when you look at a mirror, it looks like there's something behind it. There's not. Okay. Well, I don't know. Maybe there is. If you have a curved spherical mirror like this, it has a radius of curvature r, this capital R. This will create a focal point such that f is r over 2. And this can also form an image. Here's a converging or concave mirror. There's my camera, see that? And then I can back it up and you can see other images where it's now not inverted, and inverted and not inverted. So that's right there. On the other side, I can have a convex mirror, which is going to be, where you can see more of it, but it's never going to make a virtual image. So here, they both have a focal length of r over 2, but this is a positive focal length, f positive. This has a focal length right there, f equals negative. But then we can still use the same equation for 1 over f, 1 over di, plus 1 over do. Now, I do have to point out, for a mirror, the object is on this side, And the image is on the side too. So positive images are over here. That's a negative image distance. If you have an image, a real image over here, would be a positive distance. Over here, again, images would be negative on that side. Okay. Yes, I went fast. It's not too fast. Okay, let's look at the chapter summary equations. This is the summary of the summary. 1, speed of light. The index of refraction. Snell's law. I guess you could say the law of reflection. Power, which is new to me. And then we have 1 over the focal length is 1 over the image distance plus 1 over the object distance. And then this, F equals R over 2. That's the focal length for spherical mirrors. That's it. I might make another presentation with some extra stuff about how you measure the speed of light and LiDAR and let's see, what's it called? AR, augmented reality, because there's some cool stuff there, and I just want to show you because it's cool. But we'll see if I get around to it or not. But that's it for chapter 25. The end.